Hello, this is Mr. S, and today we're going to go over some fundamental science concepts as review. Chapter 2.1 is what do scientists do? And the concept 2.1 here is that scientists collect data and develop hypotheses, theories, and laws about how nature works. All right. We're going to be reviewing scientific method. The whole of science is nothing more than a refinement of everyday thinking. And I meant to put that's Albert Einstein there. So a good example of scientific method in action was that core case study where scientists use the scientific method to see how clearing forested land can affect its ability to store water and retain soil nutrients. So if you didn't read that, go ahead and go back and read that. They designed an experiment to collect data or information to answer the question, and from the data they collected, they proposed the scientific hypothesis, a testable explanation of their data, right? And so land cleared of vegetation and exposed to rain and melting snow retained less water and lost more soil nutrients. So then they tested that hypothesis twice, and the first set of data measured the amount of soil nutrient nitrogen in the runoff water, and then they repeated their controlled experiment to determine the amount of soil nutrient is phosphorus, and then they ran both experiments to confirm their hypothesis. So here you have the scientific method as a review, so if you want to pause the video and go through it at your own speed, but basically you identify the problem, you find out what is known about the problem, ask a question to be investigated, and perform an experiment to answer that question and collect data, analyze the data and look for patterns, and this is where you can see a scientific law happening, if it's so clear there. You can propose a hypothesis to explain it, use hypotheses to make testable projections, and then perform an experiment to test the projections. So either it's accepted, revised, or you can make it more testable and test again to revise and come up with different ways until you find out if your hypothesis is accepted. And that can become a theory, which we'll talk more about soon. So again, here's the example of the case study. And they were measuring the loss of water and soil nutrients. So they were comparing a site that was totally deforested and a site that was natural. So that would be the control. All right. So scientists are skeptical and they demand evidence. And I just want you to know that these are some of the most rigorous and credible scientific journals. And there's a lot of really good, credible scientific journals, but it's really important to think about where these are coming from and which journals are publishing really good science. So the people that conducted the case study about the deforestation, they described the research and submitted it to a journal for publication. And that's really what scientists do. But before publishing the articles, the journal editor had them evaluated by other scientists in their fields, and they go through a really rigorous process of analyzing their research and seeing if it's valid. So then you have scientists in your field and scientists in the greater community really analyzing and making sure that it makes full sense and that it's extremely valid. And then after that, further research on top of those reviews strengthen your argument. And so an important part of the scientific process is peer review, and it involves these scientists publishing details of the methods they used and the results of the experiments and the reasoning behind their hypothesis for other scientists working in the same field to evaluate. So scientific knowledge advances in the self-correcting way, with the scientists questioning and confirming the data and hypotheses of their peers, and sometimes new data and analysis can lead to revised hypotheses. So people get really, their work gets really sifted through and really scrutinized before it goes anywhere. And then we should never take a scientific theory lightly. It has been tested widely, it's supported by extensive evidence, and it's accepted as being a useful explanation of some phenomenon. by most scientists in a particular field or fields of study. A lot of people say, oh, it's just a theory, but a lot went into making sure that it's an adequate theory. Science has a lot of validity to think about, right? And so another important reliable outcome of science is a scientific law or law of nature, which is a well-tested and widely accepted description of what we find always happening in the same way in nature. An example is the law of gravity. So after making many thousands of observations and measurements of objects falling from different heights, scientists developed the following scientific law. All objects fall to the Earth's surface are at a predictable speed. And scientific laws cannot be broken. So this is just like kind of things that we know to be true, right? And so science does have limitations, right? And first of all, science cannot prove anything absolutely because there's always some degree of uncertainty in measurements, observations, models, and the resulting hypothesis and theories. So instead, scientists try to establish that a particular theory has a very high probability or certainty, typically around 92 to 95%. So scientists will never say that something has been proven, and instead they say something like, overwhelming evidence from thousands of studies indicates that people who smoke regularly for many years have a greatly increased chance of developing lung cancer. A second limitation of science is that scientists are human and not always free of bias about their own results and hypotheses. However, the high standards for evidence and peer review uncover a greatly reduced personal bias and falsified results. So that's extremely small and very rare. Usually it's not bias. A third limitation is that many systems in the natural world involve a huge number of variables with complex interactions. And this makes it too difficult, costly, and time-consuming to test one variable at a time in a controlled experiment, such as the one described in this chapter's case study. So to deal with this, scientists develop mathematical models that can take into account the interactions of many variables and run the models on high-speed computers. And in addition, science and engineering products can fail and teach us lessons. So we learn by mistakes and statistical data, right? And then 4, the limitations of science involves the use of statistical tools. That's the 4th limitation of science. So for example, there's no way to measure accurately the number of metric tons of soil eroded annually worldwide. Instead, scientists use statistical sampling and mathematical methods to estimate such numbers. Despite these limitations, science has the most useful way that we have of learning about how nature works and projecting how it might behave in the future. So it's super important, especially at a time like this when there's so much distrust in science, with the pandemic and all sorts of things that we have going on, climate change. Okay, so here's your chapter 2.1, checkpoint for understanding. Go ahead and fill this out and see if it made sense. Good luck.